welcome everybody. I'm very happy to welcome Adam Koberinski, who is a graduate student at the University of Western Ontario, or in the newly branded Western University, or Western just, I guess, and the resident member of the Rotman Institute for Philosophy in London, Ontario. And he has studied originally physics and I think as a minor philosophy at the University of Waterloo, and then moved down the road to London to pursue his graduate students, where he's working with Wayne Myrvold and Chris Mink. He has a number of publications already in various journals forthcoming, and some recent ones that were published. And most importantly for this occasion, of course, he is one of two prize winners for the annual Beyond Spacetime Essay Prize competition, the other one being David Wallace of the University of South California. So without further ado, I'm very happy to give the floor to Adam, who will be talking about problems with the cosmological constant problem. Please, Adam.
Thank you. Well, that's quite the introduction, so thank you. Yeah, so I'm going to be talking about so these in the right spot, yeah. Okay, the paper that won the essay prize, so it's problems with the cosmological constant problem. Given the audience here today, I assume that some of you are all at least aware that there is a cosmological constant problem, but I'll give a quick refresher to start anyway. So the structure of the talk is going to be as follows. I'm going to tell you what the cosmological constant problem is as standardly treated, kind of disambiguate a couple different problems, and then all get lumped under the same heading of the cosmological constant problem. And then I'm going to look at so my paper has 4 steps. I kind of moved one into solution strategies for this talk, but I'm going to look at the 3 steps to formulating the problem that I take issue with. So the structure is you need all 3 of these steps in order to actually have the cosmological constant problem make sense. I am going to propose some arguments against each of the steps. So if you take any of my arguments seriously, that should be enough to block an acceptance of the cosmological constant problem. And then I'm going to look at some attempted solution strategies and why they don't. Well, so why some of them are misguided in taking it seriously, and why some of them just seem to ignore it. But to start, what is the cosmological constant? Why do we need it? It's a parameter in our best cosmological models, the lambda CDM model. The lambda is the cosmological constant. But just more generally, given a Friedmann-Lemaitre-Walker model of the universe, if you have a certain critical accelerating expansion, that indicates the presence of a cosmological constant term, a non-zero term in the Einstein field equations. So this is just a constant. It's just this term here. It's a constant proportional to the metric. From our best data we have, I actually don't know if this is the best data at the moment, but the most recent data that I found after a quick search is that the proportion of curvature compared to the critical curvature of the universe, so if omega was 1 for everything, that means you have a flat universe that's perfectly expanding, which is kind of what evidence supports right now. So if that's the case, the contribution from the cosmological constant makes up about almost 70% of the energy density in the universe, and the actual value for the cosmological constant, lambda, based on this data, is 4.33 times 10 to the negative 66 electron volts. So it's a very small value. So given that that's the case, we have a cosmological constant in our best models of the universe. What's the problem with it? Well, the cosmological constant problem, as standardly formulated, is a conflict between general relativity and a supposed prediction from quantum field theory. Turns out that the vacuum energy density, or its expectation value in quantum field theory, plays a role that could be formally treated as a cosmological constant. But when you try to insert it into the Einstein field equations, as if you assume that there's energy density in the vacuum, GR tells us that it should gravitate in some way. So when you try to insert that into the Einstein field equations, it looks like a term proportional to the cosmological constant. The only problem is there's a huge discrepancy between what would be predicted in any reasonable way from quantum field theory and that term of order 10 to the negative 66 electron volts from the previous slide. So how big of a discrepancy is this? We look at Weinberg here. He was one of the kind of people that first popularized the cosmological constant problem in this paper in 1989. That it's 120 orders of magnitude is the difference between what's predicted from quantum field theory and what is actually observed. Or at that point, it wasn't what was observed, it was the upper bound of what could be compatible with observation. At that point, they thought it was 0 still, I think. But so Weinberg, just here's a quick motivation. I think the beginning is kind of important. Perhaps it is for want of other crises to worry about in theoretical physics that interest is increasingly centered on one, which I'll disagree with, a veritable crisis. He thinks this is one of the true crises that we can really articulate in theoretical physics at the time. That expectations for the cosmological constant exceed observational limits by 120 orders of magnitude. That seems like a pretty terrible prediction. But 120 orders of magnitude isn't the only way you can sort of formulate this. As I'll get to later, depends. The value of the energy density that you predict from quantum field theory depends on where you take the domain of validity of quantum field theory to be. So 120 orders of magnitude is if you take it up to the Planck energy. Looking at something a little bit more conservative, taking the cutoff to be at what the current, or on the order of magnitude of current energies of the Large Hadron Collider, to be, you get a discrepancy of 50 orders of magnitude. So it's quite a bit better, but it's still off by 50 orders of magnitude. It's not so great. So that's sort of the way this problem is standardly brought up, that there's a discrepancy between something that's predicted by quantum field theory and what's observed in GR. It's not the way everyone thinks of the cosmological constant problem, even amongst those who take it seriously. So this is a long quote from a series of lecture notes on cosmology. So it says, in some respects, the biggest problem with the cosmological constant problem is that it's rarely stated properly. Why is the cosmological constant so small? Why is it not Planckian? Why is it not 0? All of these questions belittle the problem. If we were to have any hope of solving it, we better be clear about what the problem really is. The real issue with the cosmological constant is not so much one of fine-tuning, but of radiative instability and the need to repeatedly fine-tune whenever higher loop corrections are included. So I'll just expand that a little bit. The fine-tuning problem, so one way of solving the cosmological constant problem is just say, well, maybe there's another contribution to the cosmological constant, we can call that the bare contribution, and it just happens to almost exactly cancel out with the contribution from quantum field theory, which sounds kind of ad hoc, but it's not that dissimilar from early renormalization techniques in quantum field theory, so it's not as crazy as it might sound. But even if you do that, predictions in quantum field theory come out in you take some quantity and you do a perturbative expansion in the coupling constant, at least for QED and the weak force. So when you make a prediction of the cosmological, or the vacuum energy that would go into the cosmological constant, what you get is it changes order by order. So you'd say that to first order, this is what we predict the vacuum energy to be, to second order, etc. The problem with the cosmological constant is that you can't just fine-tune it once and have it go away. As you include higher order correction terms, you have to repeatedly fine-tune because these do not diminish appropriately with the expansion. So you have to, at every order, you have to fine-tune again. It's not stable under fine-tuning. So this is one way. Another way of making the problem works. Is there even a problem? Is obviously a view that I agree with, as you can tell by the beginning of my talk. This is from Bianchi and Ravelli, a paper from 2010 called Why All These Prejudices About Constant, or something roughly like that. That there is no great mystery in an accelerated expansion of the universe. This is a phenomenon which is clearly predicted and simply described by well understood current physical theory, namely GR. It is well understood, So GR naturally includes a cosmological constant, and the common theoretical objections against this interpretation of it just being a constant term and not being due to the quantum field theory are either weak or ill-founded. So to sort of agree with that, but for different reasons, here's kind of the main point of my talk. That the cosmological constant problem, as any of those statements, kind of, you can take it to be any of those, is a pseudo-problem in quantum gravity. It's ill-motivated from the side of quantum field theory, and one has no reason to include it in the vacuum, or include the vacuum energy density in the Einstein field equations. So sort of upshot of this is that any attempted solution to the problem will have to be a dissolution, and won't be taking the problem seriously. So even with that, there are still some variations to the problem. The old cosmological constant problem is just, they thought that the cosmological constant should be 0, so why is it not 0? Why does quantum field theory give us this huge prediction? You might think that's not so serious. Okay, if it's supposed to be 0, then we can just say we're misunderstanding something in quantum field theory and it just shouldn't contribute at all. Or you'd say what cancels the contribution from quantum field theory. By the way, this rho, that's just the energy density of the vacuum. I think I told you lambda was the cosmological constant already. The new cosmological constant problem, now that we have strong evidence that it's not 0, is taken to be more pressing by physicists, or by most physicists. I don't quite see why. I think we were talking about this privately earlier, but that there's an almost cancellation. Why, it's almost 0, so what almost cancels the contribution from quantum field theory? There's a sort of naturalness assumption here, I think, that if there's gonna be something that's canceling this huge contribution, 50 orders of magnitude, it should just cancel it to 0. There should be some exact cancellation. But I mean, if in both cases it ends up being fine-tuning, whether you're fine-tuning to 0 or fine-tuning to some other number seems roughly the same to me, but that's sort of beside the point. And then, so I'm not going to be talking about the coincidence problem, which is sometimes lumped in with the cosmological constant problem. It's just that why do we find ourselves in an era when the energy density from the cosmological constant is roughly proportional? It's bigger than, but on the same order of magnitude as the energy density from ordinary matter. And by ordinary matter, I mean that includes dark matter too. So one's about 70%, the other's about 30% of the total density. Sometimes that gets lumped in. There's a whole literature about this sort of stuff, but I'm going to ignore it for now. And in both the old and new cosmological constant problem, you can formulate it either in terms of fine-tuning or what is taken to be the more pressing radiative instability. So with a quick whirlwind tour of the cosmological constant problem, now I'm going to go into a little bit more detail of how one actually formulates it and criticize each step. Like I said earlier, so there are 4 steps. Like I said, I don't really have anything against the 4th step, so I've included it as a segue into the attempted solution strategies, because that kind of naturally leads into that anyway. So I'm going to outline each step, provide a criticism of taking that step seriously, and any one of these objections is sufficient for not taking the problem seriously. So step 1, there's apparently a prediction of quantum field theory that this is a huge vacuum energy contribution. What grounds do we have for taking that as actually true? So another way of framing that is, where does the vacuum energy come from in quantum field theory? So I'm looking, just to make these equations compact, I'm looking at a scalar field. It generalizes to all other sorts of fields in quantum field theory as well, so there's nothing particularly special about the simple case in the scalar field here. But you start with to get a quantum field theory, you start with the classical action of a field theory, classical Hamiltonian density. You can formulate all these sorts of different things. Hamiltonian density represents the energy density, which is why it's here and relevant. Then you go through a standard quantization procedure, and then your Hamiltonian, the difference between the Hamiltonian and the Hamiltonian density is that this one it's a quantum operator versus classical, and it's been integrated over space. So you get the energy density is similar in form to a sum of harmonic oscillator modes of creation and annihilation operators. In quantum field theory, these are roughly what create excited states at a given momentum. To the quantum fields, whatever those are, that's a whole separate topic. Then you have this term here, which, so this is one case where the scalar field example makes it more compact, but obscures things a bit. This can, at least this part can be transformed away in a scalar field by a process called normal ordering, which is just a way of ordering the operators, such that a term like this would cancel out. You can't do this generically in quantum field theory, so I've left it in certain gauge theories like QCD. Normal ordering spoils gauge invariance, and there's at least some controversy as to whether it's an acceptable step. But in either case, this term here, as a whole, diverges. You have what's here basically an infinite sum of sort of 0-point energies associated with these oscillator modes, and then you have an integral over whatever this potential is. You have an integral over all of space. If you're taking this to be generic to all Minkowski spacetime, then you've got a problem because you're integrating over an infinite spatial region. So it's divergent. Usually how we remove the divergence, like I said, there's a process of normal ordering in this case, but more generically you can place the quantum field theory in a box or give some appropriate boundary conditions such that you're not integrating over an infinite extent of space. And then you can maybe put it on a lattice, do something like that, to sort of, you get rid of some of the, you can discretize things and then cancel them out. So this term then becomes finite, and then you just subtract it off. What you're interested in quantum field theory are energy differences. So you can kind of, if you're saying that, what we want is differences between the vacuum and excited energy states, you can just take the vacuum energy expectation value to be 0. No predictions from quantum field theory are going to depend on what exactly that value is. In another formalism, that's sort of one way of looking at quantum field theory, but I think a nice representation of what vacuum energy would be in quantum field theory is by looking at Feynman diagrams, which are just pictorial representations of turns in an expansion of one of these perturbative expansions for example, a scattering amplitude, 2 electrons hitting each other and producing some sort of interaction and scattering off. So vacuum diagrams, or vacuum energy diagrams, show up as these bubble diagrams which have no external legs. See how they're just kind of closed in on themselves. External legs represent, in a Feynman diagram, the incoming and outgoing particles. So these would be things that do not couple to the incoming and outgoing particles. You can formally separate the terms in an expansion corresponding to vacuum diagrams. They become just a multiplicative factor, and they occur in both a numerator and a denominator normalization term, and so they just cancel out. So it's just another way of saying they don't impact any of the predictions. If these things represent actual physical vacuum energy, they don't represent anything that influences our predictions in quantum field theory. So what I'm just saying, if you're aware of some of the literature in quantum field theory, is somewhat controversial. There are some effects that people say show the reality of the vacuum energy. The two big ones are the Casimir effect and the lamp shift. The Casimir effect is a picturesque way of looking at it too. So you have the way it's kind of standardly presented is with these two neutral parallel plates. They're not charged. This isn't just like classical capacitors. But the way it's sort of, they feel a slight attractive force, and this is the Casimir effect. What happens, or the way it's often described is that these plates restrict the modes of vacuum energy excitation in between the plates, and so you have fewer allowable modes in some sense in between the plates. So they're it's being pushed on from the inside by less than on the outside because there aren't those restrictions of modes. And so that therefore it's the pressure from the vacuum, or the pressure differential from inside and outside the plates that's causing this attractive force. At least that's the way it's standardly talked about. And I just showed you this diagram, but recall this is what vacuum energy would be. what you're seeing, even in that sort of picturesque version, is something to do with the vacuum, if at all, interacting with those plates. They can be represented as a collection, a really big collection of particles that are presumably could be modeled in quantum field theory. So there's still no external legs on these. What would count as vacuum energy, or strict vacuum energy, would have to have, can't be part of the Casimir effect, because those walls on this slide would be represented by external legs in these diagrams. More generally, what you're getting in both the Casimir effect and the Lamb shift. The Lamb shift is an energy correction to the interaction between a proton and an electron in a hydrogen atom. There's a slight shift in energy levels that's due to a higher order quantum electrodynamic correction. But what you're getting in here is just fluctuating vacuum energy. So we don't have evidence for a particular value or just bare vacuum energy. It's only that the matter that we can detect interacts in some way, maybe polarizes the vacuum, but there's still all you're getting is the evidence in that there are fluctuations to what's going on in the vacuum, but you don't get any sort of evidence for a particular bare energy. Just by definition, you can't. You'd have no external legs to detect it. There doesn't seem to be any way that you could detect it, except, so I'm going through that there. At best, they provide evidence for fluctuations. The only evidence that you could really get for a non-relational quantity of vacuum energy would have to come from something, a theory like GR, that has an equivalence relation that all energy gravitates, and so it's not just energy differences that matter, it's the actual absolute value of the energy. But given that you already need to combine it with GR to then even motivate this first step of the problem, it then seems weird that by getting a horrible prediction from GR, you would say, oh look, this is evidence that the vacuum does have a lot of energy, and yet somehow needs some new way of being canceled out. So that's why I don't think you should really take anything from quantum field theory to give you evidence for a magnitude of vacuum energy. But let's say you do. Let's say you say, okay, I disagree with everything you just said, or I'm not convinced, so let's move on to the next step. So quantum field theory predicts that we have some quantity of vacuum energy, some absolute quantity. What is that prediction? Given that there's all these discrepancies between what's observed and what's predicted from quantum field theory, there has to be a numerical prediction of some kind. Like I said, to get rid of the vacuum energy, it's usually a renormalization procedure, some sort of way to render those quantities finite and then sort of cancel them away. This is a rudimentary renormalization procedure. There are more sophisticated ones that are used in quantum electrodynamics and all of quantum field theories to cancel divergent terms, more or less cancel them. And it turns out there's a principled way of being able to do this. If renormalizable terms in a quantum field theory can be canceled such that you make a redefinition of terms at some finite order, and then at higher orders, you've sort of removed the problem. Once you've done it once, you've done it for all orders. So you can sort of introduce, for example, in the cutoff renormalization procedure, you can introduce a cutoff, redefine some of the parameters, like in QED, you can redefine an electron's mass or its charge to factor in the bare divergent charge, and then you can take that cutoff then to infinity again, and you've kind of protected your terms by redefining certain parameters in the theory. This is a property of things that scale. Scaling logarithmically is very easy to deal with. There are ways to deal with slightly more complicated things, but anything that any parameter that scales quadratically or higher is non-renormalizable. It turns out the vacuum energy density is not renormalizable. It scales quartically with the cutoff. So if sigma is your cutoff momentum, the energy density of the vacuum is proportional to that cutoff to the power of 4. So what that means is that you just can't renormalize it and redefine the parameter and have it be safe. This is the sort of radiative instability that I was getting at earlier. So the way most people motivate the cosmological constant problem is to say that, well, yeah, the vacuum energy density depends on a cutoff, but for any reasonable choice of a cutoff, you can take it to be the Planck scale as Weinberg did, you can take it to be the energy scale that are capable of being produced with the Large Hadron Collider. You could even take it to be as low as the mass energy of an electron, which we think, okay, we have pretty good evidence that quantum electrodynamics at least works. I mean, I think we have good evidence that it works up to the LHC, but even if you were skeptical of that, it definitely works pretty well up to the scales of electron energy. Whichever one you take, you're going to end up with a vacuum energy density that's much, much larger than the observed cosmological constant. And I'd say that the relevance of the choice of the cutoff shows that the problem's a robust one, and that no matter where some sort of cutoff is chosen to be, you're going to have this problem. Therefore, it's a generic problem in quantum field theory. This is made worse by the sort of, or emphasized, I should say, by the modern view of quantum field theories as being effective field theories. So they have some prescribed domain of validity. People don't think the standard model is going to be valid at all energy scales. There's sort of a built-in, and we think the cutoff represents a built-in accuracy for it. So there is going to be, we get some successor quantum theory of gravity. It'll tell us where, at what point there's significant divergences or between the standard model and the true physics. So they say there's some physically motivated, although not yet known, cutoff energy, and it's clearly going to be higher at least than this one, almost certainly higher than this one, maybe even somewhere around the Planck energy, who knows. But whatever it is, it's going to be somewhere that it's going to put a principled cutoff in quantum field theory, and that's going to, the vacuum energy density will scale whatever that cutoff is, and you'll still have the cosmological constant problem. One problem with that sort of motivation from the effective field theory point of view is that what usually happens in an effective field theory when there actually is a cutoff scale, so something like the Fermi model of weak interactions, which models very low energy weak interactions like beta decay, where you can basically treat it as though there are no intermediate vector bosons. Once you know the cutoff, what happens is that cutoff comes in as a suppression factor for certain terms. So certain non-renormalizable terms will be weighted, they'll be kind of dampened by the cutoff. So, for example, in this case, you'd have some ratio of vacuum energy density over the cutoff. And so there's no indication that every successor theory of quantum gravity will have this sort of feature, have a suppression factor. And even if it does, it's going to have to be a big suppression factor. Like I said, the vacuum energy density scales as the cutoff to the power of 4. So it's going to have to be a suppression factor of obviously something larger than that to make to sort of cure that divergence. And there's no way to show that that'll happen generically without assuming certain features of your successor theory already. One that, just at a bare minimum, that it's going to have cutoff suppression factors of sigma to the power of 5 or greater. So, and in any convincing argument supporting that, you have to assume some sort of class of high energy successor theory. Since the cosmological constant problem is supposed to be this generic problem that's motivating all research into successor theories of quantum gravity, as the Weinberg quote mentioned, it seems it sort of undermines part of the motivation, at least, to have to assume certain features of that class of successors in order for the cosmological constant problem to even have relevance to current quantum field theory in GR. A bigger problem that I think comes from this effective field theory view is that the effective field theory view of quantum field theory is based on renormalization group flow analysis, that certain parameters become irrelevant at low energies, and so that any successor theory will look sufficiently like a quantum field theory at low energies. This really depends on having a clean separation of energy scales away from some critical point. So generically, this is supposed to be you can separate the high energy physics. That's sort of the qualitative lessons. You can separate the high energy physics from what's going on at the comparatively low energies in quantum field theory, because the physics at that scale is sort of irrelevant to the physics at the scales we're looking at, except for maybe fixing some empirical parameters. So one problem with that is there's some controversy over the applicability of scale separation regarding the cosmological constant. Even looking at it the standard way, this is supposed to be a uniform energy, something like a uniform energy density throughout space that is supposed to only really be relevant on cosmological scales, which are huge length scales and therefore very low energy scales. To assume that really, really high energy physics is going to give you some generic solution to this problem is to then say that those scales don't separate very well. Something at very, very high energies and very small length scales is going to become highly relevant, apparently, to low energy, like large length scale physics. And I mean, it doesn't get any larger length scale than the cosmological constant scales. That's looking at the scale of the whole universe, or at least the Hubble volume. And another thing that I'll get to later is some solutions, some of the attempted solution strategies explicitly violate scale separation, even if you're not convinced that there's some controversy there, and therefore undermine the problem they're trying to solve by coming up with a solution. So, yeah. So just to recap again, there's a cutoff dependent vacuum energy from quantum field theory. Goes up with the fourth power of the cutoff. The effective field theory view depends on some separation of scales, which is probably undermined by taking the vacuum energy density to even be relevant at all for the large scale cosmological constant. And just as a sort of general point, divergent, non-renormalizable terms in quantum field theory have never been taken seriously until there's been some convincing mechanism demonstrated to suppress them or to cure the divergences. I don't think that the vacuum energy density should be any different in this case. We shouldn't trust it until there's some mechanism for suppression. Okay, so I've told you quantum field theory doesn't require a particular vacuum energy density value, and that it also doesn't predict one. Given that you disagree with both of those, maybe now we should wonder how the vacuum energy density should actually enter the Einstein field equations to actually get to the problem that assuming we've come up with a prediction from quantum field theory, and you don't take my argument, those previous arguments to be convincing. Now we want to take that predicted value and somehow plug it into GR to actually relate it to the cosmological constant. So for the vacuum energy density to be relevant, it has to couple to the metric in some way through, one way of doing this is through the Einstein-Hilbert action. The standard way of coupling fields together in quantum field theory is a process called minimal coupling. So what you do, I mean, this is a sort of, it's a slightly more formal thing, but heuristically you can just kind of, okay, we introduce some linear proportionality between the vacuum energy density and the Ricci scalar. It's called that constant of proportionality alpha. And you just take that smoothly to 0 and see what results. In this case, you can literally just cancel it out. Taking it smoothly to 0 just means it's gone. So you have a term corresponding to the Ricci scalar, a term corresponding to the vacuum energy density. And the minimal coupling now is just through the Lorentz invariant metric. So this root G here is the only thing it's minimally coupled in the sense that that's the only thing coupling the vacuum energy density to gravity. And when you do that, and then you go through the standard process of doing varying the action and taking the stationary point, you see that you can associate with the vacuum energy density a stress energy tensor that is the density just times the metric. The sign convention depends on exactly what signature you're using, so that's kind of not super important. So the standard way, like I said, minimal coupling works in quantum field theory. This is how we've come up with interactions in field theories since, QED. So the natural extension would be to continue with that in merging quantum field theory and general relativity. The other argument is, so if you're going through this formalism, even if you introduce more complicated couplings, as long as you're doing it the same sort of way, the minimal coupling term will be like a 0th order contribution to that if you're going sort of order by order. And so that term is going to arise regardless, and so we should take it seriously. So the argument goes. But there are different paths of merging quantum field theory and general relativity. So the way I was just describing is to take quantum field theory on flat Minkowski spacetime, look at the properties of the vacuum energy density based on that spacetime background, and then try to plug it in to the Einstein field equations, take curvature into account after the fact. Another way of doing it is to take quantum fields and try and place them on a general relativistic spacetime background. So this is doing quantum field theory on curved spacetime. It turns out that you don't get any things that look anything alike by doing taking the first step, as I just described, or by doing quantum field theory on curved spacetime. So Hollins and Wald have done a lot of this. There's a bunch of papers with it. It's sort of an axiomatic formalism where you're kind of defining what a quantum field theory would have to look like on a generically curved, well, not quite generically, it has to be globally hyperbolic, but otherwise generically curved spacetime background. So this kind of looks at, do we, the standard way is treating GR as an extension of quantum field theory. Like you perturb the flat Minkowski background, you're perturbing that, and that's what causes the gravitational interaction. Whereas here, you're taking GR classically seriously first, and then trying to put quantum fields on that background. And in doing that, there's some interesting properties. One, you don't get a well-defined vacuum state even in curved quantum field theory on curved spacetimes. So obviously you're not getting vacuum energies if you're not getting a vacuum state. So that it's defined in a bunch of different ways. These sort of renormalization procedures that go into defining fields on non-Minkowski backgrounds just forbid a vacuum energy density at all. So people who kind of take this sort of point of view for how the best way of taking a step towards quantum gravity is to say, well, there's a lot of special properties of Minkowski spacetime. It's highly symmetric, and there are certain things like the form that the vacuum energy density should take. So this form is really dependent on first doing this on a Minkowski background and then replacing your etas with g's. You can't say that the vacuum energy density will have a stress energy tensor like this unless you assume that highly symmetric background. So basically there are multiple ways, if you're going to try to merge these two theories, there are multiple ways to do it. The sort of standard way of doing it, if you're going to take the other steps seriously, leads to a disastrous prediction, supposedly. The other one doesn't, and sort of explains the problem away. So it's just fluctuations to vacuum energy that are important, and not the expectation value itself. So even if you decided to do a minimally coupled sort of approach, you might say, well, maybe I shouldn't just introduce the expectation value of the vacuum energy density. Maybe that's not the right thing that I should be putting in there. It's semi-classical, so we can't just put the full, whatever the vacuum energy is, because it's going to be highly fluctuating. But maybe we take the variance, for example. There are some recent arguments which are somewhat controversial. They were poorly received at our cosmology workshop that we had at Western in June. But there's at least an argument, a qualitative argument that you could put forward that our disagreements were about the technical details. So you can think about, just in a qualitative sense, if we expect the vacuum energy to fluctuate very highly and to be on the same order of magnitude as the square of just the expectation value, or even higher, but at least on the order of magnitude, then it's a poor first approximation to just plug in an expectation value to the Einstein field equations. So as I said before, if you want to do other ways from minimal coupling, you don't have to do minimal coupling. You can try quantum field theory on curved spacetime backgrounds. You could try some other approach to try to merge quantum field theory and GR. And it seems like at least in the ones that have been tried, the cosmological constant problem doesn't arise. Yeah. So the minimal coupling even doesn't require a direct insertion of the vacuum energy expectation value. If you took something like the variance or something more complicated, you'll end up with at least a very different prediction for what the vacuum energy density should contribute to the cosmological constant term. And that paper that I referenced that I said was controversial, they showed that it's a very it's a near zero. It was a sort of qualitative theoretical argument. So it's something compatible with what we would see. So those are the steps that I take issue with. One sort of final step of taking the cosmological constant problem seriously is to argue that there aren't any other contributions from known physics to the cosmological constant that we observe. So this term kind of looks like a cosmological constant term. If you were to take it seriously and insert it into the Einstein field equations in all the ways I just said you shouldn't. But there could be other terms that look just like it. It could be a sum. Who knows how many terms it could be. So the reason I say this leads into attempted solution strategies is, at least so far, we don't know of any terms in known physics, whether it be, there are some arguments for other classical extensions, like including an extra scalar field into GR. But again, it's still new physics, whether it's classical or quantum. So the next natural thing is, if this is the only thing we know of, maybe we should search for these other terms. I think if you've got this far and you reject all my other steps, obviously go ahead and search for other terms, but I don't think you should get there. So just looking for other terms to cancel that out. How much time do you have?
About 10 minutes, maybe.
Okay, so I'll just go quickly through some of these attempted. It's some attempted solution strategies. This is sort of a little bit of an extension. So some of the ways that people try to take the problem seriously and then find a way to get rid of it. I'll look at two of those and then one that just dissolves the problem. So having some sort of mechanism that protects the vacuum energy, that besides just being suppressed by some cutoff energy. So there's a notion known as technical naturalness that says that if there's some symmetry in a quantum field theory that's broken at some energy scale, and a term that would be zero if that symmetry was restored, there's an upper limit on what that value could actually be, which is dependent on the energy scale at which the symmetry is broken. So this would be another sort of mechanism for providing an upper bound for the vacuum energy density in quantum field theory. This was a big candidate for a long time with supersymmetry, which is basically saying that all matter that we know of, bosonic and fermionic, have supersymmetric partners. So for every known fermion, there's a supersymmetric boson partner that has the same properties except for mass. And what happens is that at the supersymmetric phase, these masses, the breaking of supersymmetry is what causes the masses to be different. When the symmetry is restored, at that energy scale, you would expect the matter and its supersymmetric partner to have the same mass. It turns out that bosons and fermions contribute to vacuum energy density with a different sign. So if every one of them had a superpartner of the same mass, then all the vacuum energy density contributions would cancel out. Which would be really great, except there hasn't been any evidence of supersymmetric partners found yet, and the energy scales, the sort of lower bound on what that symmetry breaking scale would be, given the most recent tests done at the LHC, it'd be far too high. That supersymmetric scale would be far too high to actually protect the vacuum energy density in any way that would help solve the problem. It's no different than just putting in an arbitrary cutoff at this point. So this doesn't really actually, it was an attempt to solve the problem empirically. It's been kind of shown to not actually be able to do so. I should say also that, this wasn't just proposed to solve the cosmological constant problem. This is future, this was supposed to be like the next sort of symmetry in particle physics that was going to be discovered. But so far it hasn't been, and even if it is, it's not going to help with the cosmological constant anymore. Another way, I mean, there's a broad class of ways of doing it, is to violate the equivalence principle in some way. One way of doing that is to decouple the vacuum energy from four-dimensional spacetime by saying it contributes to curvature in higher dimensions, but there's some mechanism for it not contributing to curvature anywhere near as much as we'd expect in our macroscopic dimensions. Another way of doing this is to provide some sort of infrared modifications to general relativity. These are low energy modifications that are supposed to change the Einstein field equations in such a way that there'd be some mechanism for canceling out. It varies from solution type to solution type, but there'd be some sort of mechanism for canceling out the vacuum energy or rendering it relevant. So the nice thing about the extra dimension solution is we get extra dimensions in string theory, for example. So you can say, well, it's not like we're just proposing new dimensions. These are coming from elsewhere. We're just saying maybe the vacuum energy only contributes in those dimensions. There are some problems with it. So based on the amount of curvature that would be needed, based on a prediction of the cosmological constant from quantum field theory, it really heavily restricts some of the sizes of the microscopic dimensions that places some major constraints on realistic string models. Another thing, it brings up a problem of you need to provide some sort of convincing argument for why the equivalence principle, if it's technically violated in 4 dimensions and only restored in higher dimensions, why it seems to hold to such a high degree for everything but vacuum energy density. It seems like a very sort of tailored solution to just sort of literally sweep the cosmological constant term away by just hiding it in extra dimensions. So the infrared modifications to GR, these are the sorts of solutions that I was getting to earlier that will explicitly violate clean separation of scales when it comes to the cosmological constant and would render the motivation for the problem that's based on a sort of renormalization group argument completely irrelevant. So it's basically self-undermining. I mean, it could be the case that we need infrared modifications to GR for other grounds, but it undermines the cosmological constant problem by proposing that sort of modification. So there's a bunch of solutions that don't take the cosmological constant problem seriously, like dissolutions. I'm just going to look at one. It's not even my favorite, but looking at quantum cosmology, where you have sort of an ensemble of states, and you just say, well, there's all of our empirical parameters that we have to, we can't predict from theory, are free parameters in an ensemble of like in a Hilbert space where there's a bunch of different universes for each quantum state, and our universe is a typical one of these quantum states. And that the only explanation for what our value is that it's somewhere within the generally typical range that's also compatible with anthropic constraints. We have to be here to see it or something like that. So what this does is it avoids the problem of talking about it doesn't bring up vacuum energy from quantum field theory at all. Nor does it really provide a mechanism, some sort of mechanism for decoupling it. It just ignores the problem, which I think is the right way to go, because if you've agreed with anything I've said so far, it's not actually a problem. So there's no need to really address it, I think, in attempted new theory of quantum gravity. Right, so that's it. Just as a quick sort of rebuttal that I've heard from actually Mike Schneider, who's a PhD student at Irvine. We sort of are both working on the cosmological constant problem. He has a slightly different view. His view is that, well, I mean, suppose it's meant to be just a guiding problem in constructing new models of quantum gravity, then it doesn't necessarily have to be a well-motivated problem. It doesn't, it can be kind of sloppy as long as it's serving the heuristic purpose of generating new models in quantum gravity. And if you're going to take this view, say, well, like, look at all the people, look at all the literature on attempted solutions to the cosmological constant problem. By that metric, it's a very successful. It's serving this heuristic purpose very well, is what we should say. But so far, none of these solution strategies that really take it seriously has led to major breakthroughs in developing a theory of quantum gravity. Many of them are either just sort of designed to eliminate the cosmological constant, or they're motivated from other independent lines that wouldn't require the cosmological constant problem to be there to begin with. And like I said, many of them don't even solve the cosmological constant problem. It's more of a dissolution to the problem. So I would sort of reject that view of the cosmological constant problem as a heuristic, or that it should serve the purpose of being a heuristic. So what to make of the problem as a whole? Given its shaky foundation, any successful solution is likely to be a dissolution, like I've kind of gestured towards. And I'd be happy too if someone were able to come up with a better formulation of the cosmological constant problem and say, no, it really is a problem. Those were sloppy arguments that you were criticizing, and here's what it looks like when you really take everything very rigorously and show here's a way that can show that this is really a problem from outside of these standard arguments that I've presented. And I'd be completely happy with that. I think a reformulation of the problem, if it were a real problem, would help to clarify, one, what the problem is, and two, potential solution strategies that might actually be helpful. And so in that sense, a new formulation that was actually one we should take seriously would be great. But what I'm saying most applies to the cosmological constant problem as has been presented for the last, I guess, 20 or 30 years or so. So that's it. Thanks, everyone.
All right. Thank you very much. So I think we should hand over to Chicago. Nick, do you have any question?
First, sorry about the lack of a camera today.
Well, we see you.
But I don't seem to be moving much.
No, you're frozen.
So, okay. Let's put my thing on. I wanted to ask a bit about the logic that came up in the second part of the talk. Exactly what the idea is of it regarding the effect, how the effective field theory idea sort of plays into the argument.
Sure.
There was one slide in particular I was a bit confused about. I think it said something like there was no reason to think that generic physics beyond the standard model would cure divergences.
Yeah, that's, I can
Like that one. Yeah, really.
It's on here.
Yeah, that's like that. So how are things supposed to be going here? I mean, one response to the problem might be, this is really a guiding principle for looking for new effective field theory physics, that this will get solved before we get to before we have to deal with quantum gravity. And then this point sort of seems to address, well, that seems not very likely, and so then that would seem to support the cosmological constant problem.
So okay, finish. If you've got more to say, go ahead.
But there were other points when you were talking where, right, you seem to be wanting to push back against that. But part of the cosmological constant problem is that we expect it will kind of carry on in effective field theory, and then this point seems to sort of support that kind of reasoning. Sorry, I hope that's
No, I think that, thanks, I appreciate the question. So I was maybe unclear. There are sort of two different points that I want to make here. This first one is basically saying the way you'd interpreted it, which is good, because that means I got at least that much across clear. So basically, you'll need, so some sort of effective field theory approach isn't going to fix the problem without making some substantial assumptions about what the future theory is going to look like. And then the second point is that the violation of separation of scales might undermine the whole effective field theory view of the cosmological constant problem to begin with. So I presented the first one first because it's a little bit weaker, and if you accept this separation of scales argument, then there's no point to bring up the first. But these are sort of two distinct issues in trying to come up with a prediction for the vacuum energy density. Does that answer your question?
I think so, nearly. So now let's just press a bit on the separation of scales argument.
Sure.
I'm getting feedback, so I'm having to turn off the sound from there. Okay, that's a bit better. So so the idea is the separation of scales argument is we just can't trust the calculations that we have now for the vacuum energy. Is that about right?
Yeah, so basically that if the vacuum energy is going to be relevant for something at such large distance scales like the cosmological constant, that sort of, and that this therefore then plays a really important role besides, the presumption is that it plays a role besides just setting whatever the value of the constant is, because that's the problem we're dealing with, is trying to figure out how to set that value. But so, given that something that's supposed to be this very high energy quantum phenomena, supposedly, of looking at vacuum energy density, if it's cured, if it could be cured by something beyond effective field theory, the fact that it has so much relevance for universe scale, like gravitational physics, is a sort of undermining of the separation of scales that's required for an effective field theory sort of view of the problem to begin with.
Okay, I think I get it. Thank you. Thanks.
Thanks.
That's all from here for now.
Thanks.
Karen?
Yeah, I'm wondering about why you're looking at the solutions, and you'd say any solution would have to be a dissolution. But even your dissolution, you wouldn't want it, right? Because you're saying there is no problem at all.
Well, yeah, so maybe it's just the confusion over a dissolution is just something that rejects the problem.
Yeah.
It
So
doesn't have to explicitly.
each one of your arguments would be a dissolution.
In that sense, yeah.
Okay.
Yeah, so this came from talking with Mike. He thinks anything that says we shouldn't even take it seriously, he calls that a solution. I just used the word dissolution as a way to make that clear as to how I relate that. But yeah, no, it's not, you don't even have to address the problem necessarily. That any future theory of quantum gravity shouldn't be a solution in the sort of narrower sense to the cosmological constant problem.
Yeah. So when you said there are other dissolutions that you're not talking about in this,
Yeah.
the one you presented, you said was not your favorite or something?
Yeah, quantum cosmology. It was just an easy example to talk about quickly. That's that doesn't really focus on the disagreement between quantum field theory and GR at all.
So then the other dissolutions, why would they be necessary when you've got your arguments anyway?
Yeah, so maybe, like I said, maybe dissolution isn't quite the term that I want here. So maybe this is, again, to appease one person. So, I would say that there doesn't need to be a separate argument against the cosmological constant problem. You can come up with a new theory of quantum gravity and just ignore it. The terminology there beyond that doesn't. That's the point that I was trying to get across. So that makes it clear.
Yeah, just a quick question. The presentation of QT curve spacetime and semiclassical gravity. So, did you say at some point that you can't really take an incremental tensor from QT curve spacetime and use it to calculate some back reaction because it's not clear what the incremental tensor would look like?
Yeah, so it's the sense is that there isn't going to be just a straightforward back reaction type solution to it. So that's in a generic space-time. Also, to formulate that, the form that the stress energy of the vacuum energy density is just proportional to the metric. That's done in Minkowski space-time, which is highly symmetric,
Okay.
and the way to argue for that depends explicitly on exact Lorentz invariance.
Okay, I understand, but it seems to me as if for practical purposes, some calculations do start with QT curve spacetime and then want to know about certain errors and plug in some kind of field from QT space in order to obtain some back reaction.
Yeah, so I guess maybe if you have more to add there.
No.
Well, so in the case, and it turns out that in doing quantum field theory on a curve, on generically curved space, or generically globally hyperbolic spacetimes, there isn't even a well-defined notion. You can't even have like, oh, here's what it would look. Here's like a slight difference of what the vacuum energy density would be, because there isn't a well-defined vacuum state, let alone any energy associated with it. So the point there is just these different, depending on which sort of approach you take to like a semiclassical first step to quantum gravity, something like a cosmological constant problem won't even be well formed. Like you can't talk about vacuum energy density at all, let alone changes to it. I mean, it could be the case that in particular solutions, you might get something like a vacuum energy density, but I don't think the quantum field theory on the curved space-time literature has really looked at that too much, so I can't say it for certain.
Okay, you will ask later. Okay.
I have a question in connection to that, sort of also concerning step 3. So the basic argument is that the cosmological constant problem doesn't really get any traction, doesn't arise in ways to combine QFT and GER, which are alternative ways and prima facie just as good ways to do that.
Yeah.
And the reason why it doesn't arise in QFT and curved spacetime is because they couldn't define a vacuum density. That's the problem, so you don't even really get started.
So there are some other related issues. So there is a particular form like point splitting renormalization, which is basically you're looking at treating quantum fields as actually being operator value distributions and taking that seriously, and then you can't just multiply distributions, which is generically true, but usually that's sort of ignored, I guess, in the normal ways of doing quantum field theory. So I can't say in all detail because I don't remember, but that sort of procedure also precludes. It gets rid of there being of certain properties in the vacuum, and then it turns out that in generic spacetimes there isn't a well-defined vacuum.
I think it's true that generally that's a big problem for that approach. They can't formulate that. But maybe what this shows, what this points is really a problem for that approach, rather than giving us a good reason to be complacent about the cosmological constant problem. So really what they should do is they should get a way to have a concept that generically is applicable to quantum fields on curved spacetimes, that defines a vacuum energy for them, the vacuum density, and then once you have all of that, etc., they all do their work. They come back to us and present how this is supposed to work in their work, in their approach, and then we see, oh my God, maybe it's even 200 orders of magnitude, or who knows? I mean, that might be one way to look at the problem there, and then true, we still have to get past step 1 and 2.
Yeah.
But maybe we can get past step 3.
Yeah. So
some move like that.
So I'm a little bit rusty. I can look. We can talk about this later too. I can look at the Hollins and Wall papers. They have a bunch of stuff, but I think part of their point is that you don't need a global vacuum state to do quantum fields. So you can have quantum fields doing things on the space-time without having some sort of global vacuum state. And they may have, I'm sure they have some sort of argument for why that's okay. But yeah, I think you're right. If it turns out that was like some deficiency in that point of view, that, okay, it turns out they can't define it, but they really need it. then yeah, I would agree. But I'm just not sure. I'm pretty sure there's a way around that. But there are other shortcomings to that approach as well. That is,
Oh yes, no doubt there are shortcomings about that approach.
Yeah.
But the point is, perhaps if people like Bob Wall and some others really finish their project and get over these problems, then maybe we'll have some version of the cosmological constant problem re-emerge.
yeah, I mean, and that's it's a possibility, I'm sure. But I think in terms of specifically looking at vacuum energy density, I don't know if that would arise. There may be some other like analogous thing in that case, but yeah.
I have one brief point about step 2. So one complaint there was that the scale, separation of scales here, right here exactly, that some solutions to the cosmological constant problem violate this, thereby undercutting, sort of like incoherence, undercutting their own motivation for solving the problem in the first place.
Yeah.
But that may just, of course, be the problem of some of these solutions. That doesn't mean there's no problem at all.
Yeah, so I mean, this is, I think that generically, there's the separation of scales is inherently, well, maybe I might need to do a little bit more work to actually provide a rigorous argument for this, but I think it should maybe go the other way, that to say that high energy physics beyond what we know in the standard model is going to give us the cosmological constant or have this cosmological relevance, that's already a major violation of separation of scales. So this was just an extra point that even, I think that's the generic argument, and this is that some of the solutions even undermine it.
That's helpful. Okay, excellent. So Nick, maybe I give it back to you. You have more questions, right?
Yeah, there was one more thing I wanted to ask about. Sorry, I was getting some feedback. Towards the end, where you talked about the problem with minimal coupling being that the fluctuations were very large compared to the background energy.
Yeah.
So, all right, so that was still step 3. But how does that help with the dissolution of the problem? Because it still seems, I mean, if you think about, most of the values are still going to be the sort of, within the variance of the whatever the mean value are still going to be large, so there's going to be a large background energy. This doesn't tell you that it's probably small.
No, so what it would, this particular paper, and I think in general, if you're looking at the variance of the vacuum energy, you're going to see it vary from space-time point to space-time point, and it's going to sometimes be above the mean and sometimes be below the mean, and so again, this is just a one proposed solution, but this paper by Wu and Yang and anyway, that paper that I'm referencing there, they argue that these, when you sufficiently when you average over a small space-time region, the net effect of those fluctuations is going to be very small. They're going to, on average, cancel each other out from space-time point to space-time point.
Okay, all right. Thanks. Sorry if you said that before.
Oh no, I didn't. So thank you for.
Okay. By the way, I didn't say before how much I enjoyed the talk. I really learned a lot. So thanks.
Oh, awesome! Thank you very much.
Baptiste.
Yes, I have a question about the last part of the talk about the motivation and what would be the normative consequences of the claim with respect to. Sorry, not yet. But the point, we want to know whether it's still a guiding principle we should use.
Yeah.
So you seem to say that because it was not successful in the past, we should stop using this guiding principle. Is this correct, or are you more neutral, just constating that it didn't work out?
So I'm saying,
or do you want to ask people to stop using that and do something else?
So I think the previous arguments are me trying to convince people to stop taking it seriously. And then this is saying, well, as long as it's spurring some creative thought, that's all it really needs to do. I think the attempts that haven't really led anywhere, plus the fact that it's an ill-motivated problem, I think are enough to undermine that. I mean, if people want it, I'm not going to tell physicists what to do and what not to do. If they want to say, well, I agree with you that the problem is ill-motivated, but I still want to try and find solutions for it, I would find that weird, but go right ahead. Yeah, that's the...
I have another question concerning step 1. So there the argument was, okay, we have evidence for fluctuations of the vacuum energy density.
Yeah.
No problem there. But it doesn't give us evidence for an absolute value of the energy. That's right. So it doesn't mean that there is no, that there presumably is some fact of the matter about the expectation value of the energy density of the vacuum, except that none of this allows us to sort of fix that, say what it is, right? You're not saying that there's no...
Yeah, so I think it's somewhat tricky. That's one way to respond to it, and I'm okay with looking at it that way. Another way is that what's happening when we represent like polarization of the vacuum is really just because it's only measured through measuring the external matter, the external lines in the Feynman diagram, is that this picturesque way of looking at things might not be telling the story of what's actually going on. It might not be that there's something is being created out of the vacuum to interact with the particle that we're measuring. It could just be some highly nonlinear effects. But I'm agnostic as to which of those. So it could be the case that there is some vacuum energy value, and just quantum field theory doesn't give it to us, and in fact it gives us a hugely divergent value that we shouldn't trust. But nevertheless, there is some fact of the matter. Or it could be that the way we're kind of representing things isn't very accurate as to what's going on at that scale, even though it generates the right prediction. So I guess that kind of leads to realism versus instrumentalism, and I don't really know what it is.
Okay.
So I tend to avoid that debate when I can.
Nick, do you have any further questions?
No, not really. That's fine, thank you.
Okay. What about other members in Geneva here?
Maybe just I want to be sure that I understood your answer to Sherry's question. So you want to be neutral, and you're saying that everything you said is compatible with two options. First option, the vacuum genuinely has a particular density energy, but it does not have a definite value, something like this.
But nothing from the formalism of quantum field theory would tell you what that value is.
And the other alternative is that there is nothing like that. It's more like a mathematical
There's something.
artifact.
That may be something that's going on. So we do have the whiteboard. There are markers. So like vacuum polarization effects would be like if a correction to the electron self-energy. If this is the electron being emitted and detected, it might. That's like a first order one, like a photon is emitted and then reabsorbed, and you have all these other diagrams where you have things like just more corrections at higher orders, and each vertex means it's got more coupling, so it contributes less and less. So, but these are pictures. So this doesn't, and I mean, there's a bunch of ways to interpret them, but even if you want to interpret them, rather than avoid, I'll just avoid that. We can say that this is not what's actually going on it's not that there's necessarily a photon being emitted. These are pictorial representations that you can then write down in the appropriate integral to figure out the observable quantities. So that's sort of an instrumentalist view rather than a mathematical artifact. More that we shouldn't take what's being represented in vacuum fluctuation corrections to be literally what's going on. And in that case, then we don't have to say that there's vacuum fluctuations even in it in some sense, and then we don't have to say that there's a value of vacuum energy. The other thing is that there could be vacuum, as a third response, is that there could be vacuum energy that exists, but there's no consistent way to give it an expectation value. That it's just so, expectation values would have to be limited to some area, and that the notion of a global expectation value of vacuum energy just doesn't make sense or something.
Yeah, I think a lot of the points you make don't depend on an answer to that. They're perfectly valid regardless. But it's still that kind of issues that are also raised here.
Yeah.
And I think, similarly with the Casimir effect, some of the similar questions about realism, I guess, at the end come up. Should we really think that there are virtual particles and that stuff really happens, or is this just happens to be for some reason or other that we don't fully understand a pretty accurate, usable instrument to calculate certain things we observe? I think these questions very much come to
Oh, they do, for sure. And so I actually had more about the Casimir effect. It doesn't quite relate, but I removed it because it was getting a little off topic. But basically, yeah, there's a way to show, you can show that picturesque version of the vacuum pressure, which is why it's often used as being more indicative of the reality of vacuum energy, because you can say like, oh look, the vacuum is acting like it's exerting pressure on a macroscopic object. You can, of course, this
Oscillation.
Yeah, but so that's it turns out that that's not the generic way of, so Casimir effects with different geometries, if you have spherical plates, will have different effects, and it can't be described that way. That it's basically the correct way to describe it is to look at treat it as like a loop correction to the interactions of matter within the plates and between the plates. And so then it's no different than the Lamb shift. And then, I raised some questions about how literally to interpret these sorts of things. But I think you're completely right that it does lead into those bigger discussions, which I enjoy.
I don't think you need that discussion to make the points you're making.
Yeah.
But I still think this is a discussion to be had.
Yeah, exactly.
Yeah. Okay. Anything else?
So there's still cosmological constant, and we still want to explain that. So that's still a problem to be solved by quantum gravity, or is it just a constant in the theory immediately?
That's not addressed by what I've been talking about, but you could look at it either way. So the Bianchi and Ravelli paper say that the most general form of the Einstein field equations have a generic constant. We fix the measurements and fix that value. We don't need more of an explanation for that any more than we need one for Newton's gravitational constant. That's not satisfactory to most physicists, and I don't know enough about the working cosmology. I think it'd be nice if we had some dynamical explanation for it, but it may be the case that it really is just a constant.
At some point you seem to say that you don't care so much whether the number is close to zero or not.
Yeah.
So it would be a difference by using zero?
It's just one of these, in the context of fine-tuning. So, the argument for fine-tuning is, look, we have to have this very precise cancellation to 120 orders of magnitude to make sure it's exactly zero. You need the exact same precision of cancellation to the exact same number of orders of magnitude to make sure it's just slightly different than zero. So there's just no difference in kind there, I think. I think the idea for it being zero is that there's going to be something like supersymmetry that could exactly cancel it out.
Yeah.
Then you don't have to explain anything. But if you're going to just look at it as a fine-tuning problem, I don't see the difference between fine-tuning to zero and fine-tuning to almost zero.
Because motivation comes in externally.
Yeah.
You think if you look at the function problem, you should be concerned with external motivations for those things.
Yeah.
But Augustine will tell you, heuristically, in the past, taking it to zero instead of a small value tends to work, right? That's the argument for this naturalist.
Yeah.
Has it
So
been useful in the past?
yeah. So there were known, like I said, the supersymmetry is a known mechanism for canceling it, at least when the symmetry is restored. Yeah. So it's it's more troubling in the sense that they didn't have a ready solution for it. But I don't think, in principle, when you look at it, it's just like a why is it this value rather than this value? If you don't have a solution in mind, there's no difference.
Yes, yeah.
What do you think is the best argument to dismiss these final diagrams as somehow ontological? Why do you read them just what's your argument?
I'm sort of unsure about that. I think, I mean, on the one hand, it's clear that this isn't exactly what's happening. There's an infinite series of these, so, I mean, it's either an infinite sum of all of them, which could be a certain path integral approach, but then our best indications are that our perturbative expansions are asymptotic series, and it has to cut off somewhere. You eventually, adding more terms is going to make it less accurate rather than more accurate. So I find that really hard to square with saying, oh, it's just the sum of all these things going on up to, whatever order it happened. Let's say it was 100th order that things start going haywire. You should interpret these realistically up to 100th order, and then we should stop caring about them at all. That's a potential motivation for that.
Okay, motivation I always have for this is that in some sense these speed functions you have as propagators, they can also develop in the classical context, right? So if you accept these as visual particles, we also have to accept visual particles developed in the classical equations, right? You probably don't want to do that. That's why I thought you would.
Yes, and there's also, I guess, with these, the virtual particles won't obey mass shell conditions and energy momentum uncertainty relations, or they'll travel fast. I mean, because there's no fact of the matter as to how they're traveling, there are certain frames in which they'll travel faster than the speed of light. So there's a bunch of problems with interpreting them super literally, but yeah, I think there are some ways around that thing. But I think the big problem is, how do we, other than them being nice pictorial representations, how do we make that more secure than just saying, oh, it's nice, it's easier to visualize this. But yeah, so I kind of lean more that way, but there might be a good way to justify this as being a more realistic interpretation. I just don't know it.
Okay, that's cool. Thank you.
Okay, please join me in thanking Adam again.